We are on section 2.1, but we have time at the beginning of class most days to go over any questions that you have. Does anybody have homework questions we should look at? Anybody look at the Wiley Plus chapter 1 and have questions to go over there? Okay, well, that assignment's due Sunday, so take a look at it between now and Friday, and then if you have questions, we can make sure they get answered so that you're not sitting there Sunday night going, Okay, we want you to get 100. Does anybody have questions before we begin? We're going to take a look at section 2.1, counting, how the pigeonhole principle leads to precision through estimation. So we're moving from qualitative to quantitative. We want to start thinking quantitatively. What does the word quantitative mean? Yes, the amount. So how many? We're going to start thinking in numbers. That's why I asked you to bring 1,000,000 items. So we don't want to just count things that are a lot and say 1, 2, 3, 4, a whole bunch. Okay, we want to be a little more precise than that. We have big numbers in the world today with how much your computer holds in bytes to how much the national debt is. We want to get kind of a feel for these numbers. How big are these big numbers? So I asked you to bring 1,000,000 items. Let's see what you came up with. Who wants to share the 1,000,000 items that they brought? What did you bring? Yes?
A salt shaker.
A salt shaker. Okay, so salt is tiny and you can fit a lot of little grains in there. Were you able to narrow down how much salt you'd need? Did you get Google to help you figure out how many grains of salt you needed?
No, I haven't got that far yet.
You haven't got that far yet. Okay, so you're going to get on Google and see how much should be in there to make up at least 1,000,000, okay? Okay, and I'll go in order here. What do you have?
I also had salt, but I Googled it, and I think it said about half a cup was 1,000,000.
A half cup? Okay, well that saved you a step. Okay, that's good. All right, how about you?
Water bottle.
A water bottle. So that's not 1,000,000 water bottles. What's 1,000,000 in your bottle?
Molecules.
1,000,000 molecules. Okay, and then did you Google that to see how many molecules were in it?
It's like 6 point something times 6,000 or whatever.
Okay, more than 1,000,000's in that. What do you have, like 3 or 4 cups there? More than 1,000,000's in there. Okay, that's perfect. And how about you? What did you have?
So I also did water.
You did water also?
I measured this out, and this is like exactly a cup.
Okay.
I found it out is 8.36 times 10 to the 24th molecules.
Oh, wow. That's still more than 1,000,000, isn't it?
Yeah.
So even a cup has way more than 1,000,000. Okay. I'll write it down, though. How much did you say it was?
8.36 times 10 to the 24th.
10 with 24 zeros. So that means you move your decimal place 24 places to the right. So you'd have the 836 and then 22 zeros. That's way more than 1,000,000. Okay. Anybody else bring something? Yes?
In a way, I brought something, but I added up all of the words in all of the Harry Potter books, the first 1 through 7.
Okay.
And it was 1,860,000.
1,860,000 in all the first 7
Harry Potter books.
Harry Potter books. Have over 1,000,000 words in them all together. Well, that'll be great. So you can just take a picture of that. Okay. And I should have been more clear. You don't go online and find some picture that says this is 1,000,000 of something. Okay. Don't send me the $1,000,000 picture. I get that a lot. But this is something you can bring. Okay. So something you can put your hands around. Anybody have anything else? These were all very good, and I'm glad you started to think about how many. We're going to continue thinking about how many in section 2.1. Oh, and I have a note to remind you. In 2.2, you need a pine cone or a pineapple. Okay, so can you please bring to class on Friday a pine cone or a pineapple? Okay, so we have pine cones all over campus here. And if you like pineapples, then you could stop and pick one up. I have a note to myself to get a pineapple too. I have pine cones in my office, but not pineapples. Okay, but the author starts off each section with a question that helps us think about what's going on in that section. The section for 2.1 has the question, how many ping pong balls are needed to fill up the classroom? How many ping pong balls are needed to fill up the classroom? How many ping pong balls are needed to fill the classroom? And oh, by the way, this million items was your class activity. So if you want to, sometime during class, we'll have lots of work in groups today. So sometime during that time, you can take a picture of your million items if you brought it, and then you can upload that as your class activity. Okay, but we are going to work on this million in this ping pong ball question. So I brought some ping pong balls, and hopefully you brought rulers. Look at this one's a happy ping pong ball. Okay. So how many of these fill up the classroom? You can see they're pretty tiny in comparison to the classroom. How could we go about figuring out how many would fill up the classroom? Yes?
I want to figure out the length of the room and the width and the height too.
Okay, good. So we want to measure the length, width, and height. Okay. Okay, and then we'll compare that with the measurement of the ping pong ball. I think for the ping pong balls, instead of trying to find their volume in terms of a sphere, we'll look at the ping pong balls and look at their volume as a cube instead of a sphere. Because that way we can think of them in their little containers stacked up here and not have a big mess, for one thing. And plus, then we don't have to worry about, you know, when you put the balls together and you put the next stack on top and they all kind of jiggle around, we don't have to worry about the empty space between the balls, which we would have to do if we just worried about the volume as spheres. So we'll just think of them in all packed up tight in their little box and think of them as cubes. So I'd like you to get into groups of about 4 people and figure out how many ping pong balls fill the room. Before that, I'd like you to take a guess. So we're thinking quantitatively. So go ahead and guess, please. Write down your guess at how many ping pong balls fill up the room. Now, I've done this before, so I'm not going to guess. But I think it's interesting if you guess. So don't just say a lot. Try and get within the correct number of zeros how many there are, okay? See how that goes for you. Guess. Write it down. All right, and then we're going to find out. We had someone in the last class get pretty close. So I'll put up this working on activity for those of the students who are watching this online. They can measure their own room while we're doing ours. And get in groups of 4, please, and I'll come around and help you get in a group if you're not in a group. So the first row can turn around and work with the second row, please, and the third row can turn around and work with the fourth row, unless, like, you already seem to have a group, right, in your third row there? Yeah, you 3? Yeah. Okay, so you 3 can be a group. Groups of about 4.
Am I supposed to take a picture of myself? So are we supposed to start?
We don't have rulers, we know how long it takes.
Literally just
Okay. Like at least a.
We don't have a ruler, I have one.
Ruler.
I'll hand out a ping pong ball.
Yeah, that's not a big deal.
That's probably about.
I'll give you a clue. You can look at the floor tiles to help you. You will have to get out and measure, okay? But you can look at the floor tiles to help you and measure them.
Someone measure the balls. I'll measure the
Okay, I got this. I'm just gonna like walk.
Which way are you counting? Do you want to count that way? I'll count this way.
Sure.
Ask where we have to measure it for.
6, 7, 8.
It's 1 inch by 1 inch.
I just walked down my road, I think. That's part of the classroom.
Tiles are pretty much put.
So I should see more people walking around measuring today, huh?
It was a foot by foot.
Yeah.
And then some. And then we have to measure just that.
And they're basically like how much
Yeah, that's, I don't know.
31 and a half.
probably like
Yeah,
we're gonna just have to like measure.
So that's,
but like we.
okay, shoot, wait. Hold on. Okay. Square feet. Okay. I was like, and that's how it comes about. Here, I'm short.
What about you?
It's okay. So much is it?
Chloe, how many
These are 2.5. I'm gonna calculate that 792.
What about like?
I said 2. So what did you find? I passed out. Just count. I passed out.
31 and a half by 28.
By 28.
31 and a half by 28.
Our room is missing this corner right here in the front. But just pretend it's there, okay?
Yeah,
So we'll figure out how many would fit if that corner was square. Alright?
So there's a half chunk on each side, so that's 1. So 28.
How are we supposed to
Wait, so it's this
Put your finger where I leave off. And we'll go by 1. Right, we'll just keep counting 1. Yes. So from here, what do you say? Like 1, 1, 2.
Wait, why we going that way?
So then
I measured the bottom of the room, which was 28.
So it's 47.
So 28 what?
So 47 and then.
Yeah.
Right down that.
And that's 8,000. And then I divided that by 12, which measured in feet. So I had to convert it to
9 and
so that way
19. Roughly, yes.
I was lost. 48 times 31.
We've measured the length. width and the height. As a cube here, and now we have to measure the length, width, and height. 1 inch by 1 inch. Okay, so if we have something that is. Yes. So, how many, so if it's 1 inch by 1 inch, 12 of those would fit into 1 square. They should fit into 1 square on the floor. Right? How many fit in a square?
The width was 32. Also go here.
If I'm wrong, guys, I apologize.
I didn't take a math class last semester.
So 144.
Let's work together. Let's work together, okay? So there's more than one way to do this. So some people were measuring how many ping pong balls fit on one of these tiles and then counting the tiles. And I imagine they would stack them up as well. I've seen others of you measuring the room, so we're going to go that route. So let's take the measurement of the room. So this is the front of the room and this is the back of the room. How big was the room from front to back? I'd like a couple answers so we can get an average in case some of you are off a little bit. What did you get? 28? 28? Okay. 28 feet. Okay. And then side to side? 31? 31 and a half? Is that from two different groups?
Yep.
Okay, 31 and a half. Okay, and I saw someone actually take a ruler and measure to the top, so that's the one we want for the how tall the room is. Is that your group, right?
Yeah, it was about 9 feet and 10 inches.
Perfect. Did anybody else have that measurement so they could confirm it? No, you were just eyeballing, okay? Okay, well, we're going to get a pretty accurate measurement here, and we're going to include that little corner. So we're going to find out how much would fit in this room if it was a perfect rectangle. So let's find the volume of the room. Let's find it in inches, though, because our ping pong ball is not very big, right? So let's find the volume in inches instead of in feet. So 28 feet by 12 inches, how many inches is that? (336 inches). 31.5 times 12 inches. 378 inches. And 9 feet 10 inches. So let's just do 9 feet and then add 10 inches on. So 108 is 9 times 12, and then you add 10 inches on, and that's 128 inches. No, that'd be 118, right? Better 118? Thanks. So we have the measurement of the room in inches. Now, how do we measure that? How do we find the volume from those measurements? How do we find the volume? Times them all together. That's right. So the volume is length times width times height. So my calculator tells me that that's 14,986,944. So that's how many cubic inches. Those are called cubic inches because they're inches times inches times inches. Right? Cubic inches. And you can picture a little ice cube, right? An inch by an inch by an inch for how many that is. How about the ping pong ball? How big was the ping pong ball? Inch and a half? Yeah, inch and a half. So if we put it in a little box and make it a cube, we can find its volume as well. 1.5 times 1.5 times 1.5. So 3.375 cubic inches. We're almost there now. Okay. So we'll just take the number of cubic inches in the room and divide it by the cubic inches of ping pong ball and a cube takes up. See what we get. Would anybody like to see the long division there? I'm just kidding. I use my calculator. Okay. So, 4,440,576. That's a lot of ping pong balls. Did anybody guess between 3 and 5 million? Yay! Good job. What'd you guess? Do you remember?
3,215,473.
Well, you're very close. Is anybody closer? Anybody within a million? That's very good. Okay, so this is how many ping pong balls would fit in this room. So we can move to quantify instead of just saying a whole bunch, and we can get pretty close. In fact, you can get close enough with this idea of using even just rough estimates to get an answer to a question you might not think you could. So the question we're going to answer next, I'll write down. So the question we're going to answer is, are there two non-bald people in the world? And you say, yes, I know the answer to that. Yes. No, keep going. Are there two non-bald people in the world who have exactly the same number of hairs on their bodies? Are there two non-bald people in the world who have exactly the same number of hairs on their bodies? Some of you are looking like, that's just gross. Okay. Well, now I would like you to decide if the answer is yes, or no, or cannot be determined. So is that answer yes, there are, or no, there are not, or it's impossible to know, that we just can't know if there are or not? So pick one of those answers, and then we will find the answer. So here's what we're going to do. We're going to count here. We're going to take your ruler and measure off a 1/4 inch by a 1/4 inch. Okay. So we're going to measure that along someone in your group's scalp, like that. Okay? So somebody right along the edge of your hair here, you can pull your hair back easily, somebody's going to, in your group, will take a ruler and put the ruler up and measure off a 1/4 inch by 1/4 inch and pull quarter of those inches hairs out. Should I put the document camera at me and aim it and show the online students? No, that's just okay. And then somebody counts the little hairs. Okay. Okay. So count. Okay. And then we'll be able to answer this question.
1/4 inch. I don't know if I want my hair. What am I having?
Are you comfortable with that? Okay, having your hands okay. Alright, I'm gonna roll it. I got it. Go for it. Alright. Hold it here.
This way.
Yeah.
And then together.
Yeah, it's a 1/4, but that's what I meant.
I don't have any of those. Well, actually, I'm doing fine here, so it shouldn't be that hard.
Yeah, like just the one that where you count in your own. You might have. What do you got? What do you count?
There goes one, see.
49.
You need someone to help you measure.
Yeah, just like I counted the ones that were like a lot of okay. That makes sense.
How many?
This could vary.
Taking a deep breath.
Oh. 49.
How many do you have? A million or
We're like 49 or 50, a couple start falling.
Yeah.
Okay, we'll say 50.
Okay.
Yeah, I know. She said okay.
Oh, wait.
I started writing notes, but then it stops at like this is one.
How many was
No. By the way,
Actually, do you think I should actually measure this?
no sleeping. Stupid ass. Hmm?
Yeah, pretty much. Other people that are like 1/4 and then 3.
Start talking on Snapchat and it keeps track of the days. Under the one. This is weird because like it happened like we were talking on the same day that we went. It's not set for 90 days technically, but I know it's set for a lot. Steve is 1,114. I have talked to Steven every single day for 1,114.
Okay, so what did you do, Kathy? Okay. Okay, thank you, all of you. All of you who let your hair be counted and who counted. I know that's not something you do every day at school. The most I heard in the quarter inch was 80. Did anybody count more than 80? Okay, we'll use 80 then. So what we're going to do is we're going to find the most hairs possible on any person. We're going to find the most hairs possible on any person. So we started by finding out what people have on a quarter inch, and the most that we found was 80. So we're going to take the most, because that's what we're looking for. Most hairs possible on any human being on the planet. And then we'll have to change that to an inch, right? Because we just counted a quarter inch. So let's take a look at it inch by inch. How many quarter inch squares are there in a square inch? That's a trick question. Good job. Yeah, 16, because they're squares, right? So you need little 1/4, 1/4, 1/4, 1/4 to make 1 inch. So in 1 square inch, we have 16 quarter square inches. So the most that we could have in 1 square inch would be 16 times 80. 1280, okay. I always have to double check everything. My compulsiveness. Okay, we got it, 1280. Now, you might say, well, we're trying to find the most hair possible on any person, and there might be someone in here who didn't get their hair counted who has more hairs on a square inch than that. In fact, there's probably someone in the world with more hairs than that, because the world's a big place. But we can be confident that nobody has 10 times that much hair. Nobody has more than 10 times as many hairs per square inch. So the most we found was 1,280, but if we multiply that by 10, we have 12,800 hairs. Nobody's going to have more than 12,800 hairs per square inch. Okay, now we just have to get down to how much square inches of skin we have. You ready? You got your rulers? No, I'm just kidding. Okay. How many square inches of skin? We have a volunteer for this. This is Bob. Bob, happily, is shaped like a cylinder. Okay. So Bob, we're going to measure Bob the cylinder, and he is a 6 foot tall person. 6 feet tall, 72 inches tall, and he's 32 inches around. So he's kind of a medium-sized person there, 72 inches tall, or 6 feet, 32 inches around. And he's a cylinder. So as you unwrap his skin, it comes off in a rectangle, just like if you took a tin can. That did sound a little terrifying. Okay. For Bob, yes. 32 inches by 72 inches. All right, let's see how much skin that is. 2,304 square inches. I didn't write the square inches. Well, that's just around the outsides of Bob. Bob also has a top of his head and the bottom of the foot here. And I'll just include 200 square inches for those. That's pretty generous. That's 20 inches by 10 inches. So that's a pretty big area for the top of Bob's head and the bottom of his feet. So altogether, for Bob's skin, we have 2,304 from around his cylinder-shaped body and 200 on the top and bottom. What does that make? 2,704 inches. Now we picked a kind of average shape, height, and width to make Bob. But there's certainly people bigger or rounder than this cylinder-shaped person. So we're looking for the most hairs we could have on a person. We'll say that this isn't a particularly large person, and there are larger people, but we can be confident that nobody has 10 times as much skin as that. Okay, so no one has another 2,704 times 10 square inches of skin. So 27,400 square inches of skin. So we use that. We're looking for the most possible hairs a person could have. So we found the most possible hairs, more than anybody could possibly have per square inch. And we found more skin than anybody could possibly have. And so now we are ready to find the total hairs that will be more than anyone could possibly have. We're finding an upward limit of hairs. Let's see. We have 12,800 hairs per square inch. And then we have 27,040 square inches of skin. So you put the commas every 3 units starting at the right, and then when you get to the second comma from the right, that's when you're talking millions. So this is 346,112,000 hairs. Did I miss any? Nope, that's what it is. Okay, so let's go back to our question. Only now we have the most possible number of hairs a person could have. So let's write that down up here. $346,112,000 hairs. That's the most possible number of hairs we could have. So our original question, are there 2 non-bald people in the world who have exactly the same number of hairs on their bodies? Now we have more information. In fact, we have a little bit more information. I Googled the population of the world, and the population is 7.6 billion. So 7.6 billion, we need, let's see, this would be millions, so I need one more set of 3 zeros there. So now we have more information. There's 7.6 billion people. The most possible number of hairs any one person could have is 346,112,000. Can you tell now, do you want to think about your answer again? Can it be yes, no, or we still cannot tell even though we have this new information? What? Yes, it is going to be yes. Does anybody know why it's going to be yes? Yes?
Because there's not enough different variations for everyone to in the world to have their own number. there has to be like overlap somewhere.
Good, well stated. There's not enough variations for everyone to have their own number of hairs. Has to be overlap somewhere. So let's see if we can illustrate that with some rooms. Okay. Well, we'll circle yes. Okay. Yes, and then we'll say why. Why must there be two people with the same, two non-bald people? Non-bald. Need another N. Why must there be two non-bald people with the same number of hairs? Why must there be two non-bald people with the same number of hairs? So it has to do with how many hairs there were possible. So what we'll do is we'll have a room allocation by hair, by how many hairs you have. So we're going to make a room, and it's going to depend on how many hairs you have. So in the first room, we put everyone with one hair, all the non-bald people with one hair. In the second room, we put the non-bald people with 2 hairs. Third room, 3 hairs, and so on. So this is what we're going to do. And we're going to make a room for every number up to the most possible hairs. And actually, this room will be empty, right? Because we said nobody has this many. So we have an upper limit here of 346,112,000. And then the room before it with 1 hair less, 346,111,999. Okay, and so on. So we have a room for all the number of hairs, and it comes out to less than 347 million rooms. We're taking 7.6 billion people and putting them each in the correct room. So you don't have enough rooms for each person to have their own room. There's just not enough rooms. If you count off the number of hairs on each person and say, you go in this room, you got 3 million hairs, you go in that room, you have 25 hairs, you go in this room. There's just not enough rooms for every person to have their own room. We have too many people and not enough rooms to put them in. This principle is called the pigeonhole principle. The pigeonhole principle. So I brought a picture of a pigeonhole desk. Has anybody seen a pigeonhole desk before? Anybody? A couple of people? My grandpa had a pigeonhole desk, and every Saturday my mother and I would go over there and help grandpa with the bills. So there would be a certain number of slots in the desk, and if there was more mail than there were slots, then you couldn't put just one letter in each slot. Some slots would have to have at least 2 letters. So let's see, if there's more objects than there are slots or rooms to put the objects, then you're going to have at least one of those slots with 2 or more objects. So we have more people than we have rooms to put them if we line them up by how many hairs they have. So at least one room is going to have 2 or more people. Let's write the pigeonhole principle out. Where did I write it? Here it is. If we have more objects, then we have boxes. If we have more objects than we have boxes, at least one box At least one box must contain at least two objects. At least one box must contain at least two objects. So this is the pigeonhole principle. We used it for a kind of a fun question that's not really something you probably cared that much about. But it is used in real life to prove different theorems. So mathematicians prove theorems, and one of the ways they can come to a concluding answer is by using the pigeonhole principle. Now, it doesn't answer specifics, right? It doesn't tell us which room has more than one person. It doesn't tell if you in particular have the same number of hairs as someone in the world. It just says that, yes, there is a pair of people in the world that have the same number of hairs. There's probably lots more than a pair of people. So the pigeonhole principle can make some questions be answered. And we're going to look at some questions that you might get asked on a quiz about using the pigeonhole principle. This isn't something you need to be able to quote, but it's something you need to be able to use. Oh wait, you know what? I shouldn't say that. I think I put a question where I fill in the blanks. We'll look at that more on the day before our quiz, okay? Okay, but we'll look at some other types of quiz questions where you would use the pigeonhole principle to answer in class on Friday, and we'll also go on to the next section then. So don't forget to bring your pineapple or your pine cone, and I'll see you on Friday.